Now you should even gotten some pop-up window, I guess. Okay, so today we have Athanassios Boudalis. He did his PhD at the University of Patras in Greece and at the LCC CNRS in Toulouse. Then he did a postdoc at Demokritos in Athens. Then he moved to Florida International University in Miami. And then he moved to Strasbourg, where he's actually still today. And today he will talk about magnetoelectric coupling in spin triangles detected by CW and pulsed EPR under electric fields. The stage is yours.
Okay, thank you, Nino, and thanks everyone for being here. So this research was trying to detect magnetoelectric couplings using a EPR spectroscopy, and to do this we needed to be able to apply electric fields in the EPR cavity. But first, let me give a very brief context of what we studied and why. So what we studied was what I'm calling spin triangles. They are antiferromagnetic triangles consisting of half-integer spins of approximately equilateral geometry. I stress approximately. And although magnetically we use the same general model to describe them, chemically they can be very, very diverse. And what is this magnetic model? I will just run to the end and give you the conclusion of several decades of research. Started in the Soviet Union. They gave the foundation of what I'm showing you. So we basically have an isosceles isotropic exchange model plus a Dzielorzhinsky-Morillas or antisymmetric exchange term. This is the scheme. This is the simplest Hamiltonian that fully or almost fully describes their properties. And when you start with the simplest, so isotropic, all J's are equal. So we have an equilateral magnetic triangle. You have what Olivier Kahn described as a degenerate frustration. You have the two ground state doublets which are degenerate. But in that case, you have no EPR spectrum because it's zero probability amplitude for this intra-doublet transition. When you break the symmetry with this term, you split the degeneracy by an amount which is proportional to this difference. And when you, I'm focusing on this ground doublet, when you introduce the Dzielorzhinsky-Morillas term, you introduce an anisotropy in this ground state. So you have G parallel, which is approximately the G of the single ions, but the G perpendicular is further removed. And the counterintuitive aspect of this is that when you have an equilateral symmetry, this G perpendicular goes to an infinite magnetic field. So you have the largest magnetic anisotropy is when you have the fully equilateral isotropic exchange. It's counterintuitive. The other interesting thing that happens is that when you introduce this Dzielorzhinsky-Morillas term, you have a chiral spin texture. So you can describe qualitatively the texture of your magnetic states with an additional quantum property, the spin chirality. You can quantify it mathematically with the scalar and the vector spin chirality. So I won't go into this here. And the interesting part is that it was Daniel Loss, a group that proposed that we can use the spin chirality to encode information and to leave the classical spin qubit paradigm. So instead of going to the spin up and spin down states, the spin projection to encode information could go the spin left, spin right, and encode information on the spin chirality. And this is insulated from magnetic noise, magnetic fluctuations, so hyperfine induced decoherence. These transitions that are of interest are not EPR transitions. It's these transitions here, which are electric dipole induced. So you need, for your spins to be able to sense electric fields so that you can excite these transitions. And so you need a magnetoelectric coupling. So there is this symmetry argument that if you have an inversion center, you should not have magnetoelectric couplings, but is the inverse necessarily correct? So if you don't have an inversion center like in triangles, is that mandatory to give a magnetoelectric coupling, and under what conditions? So to test what happens in spin triangles, a nice pair of systems that we studied was this basic iron and chromium 3 carboxylates. So you have here iron 3, which is a spin 5 half ion, chromium 3, which is a spin 3 half. And the EPR spectra of these systems are quite different. So you have very strong antisymmetric terms here, and an important magnetic asymmetry, delta J. In this, the opposite is the case with the chromium complex, which has a very small antisymmetric term and a very small asymmetry. It's very close to the equilateral case. The conceptually simplest experiment that one can do is just put the sample, a crystal, single crystal, in between two electrodes and see what happens when we apply a strong electric field. So this is what the first series of experiments were. This is the crystal of the iron triangle. Very nice shape, helped a lot for manipulation and orientation. And these are the silver electrodes. And by going to 2000 volts, we're able to go to close to 10 million volts per meter and see what happens. And what you see is that as you increase the voltage, you increase the intensity of the EPR transition. So these are in two different orientations. And how we interpreted this was to consider that in the triangle outside an electric field, you have a specific magnetic symmetry, J1, J2, J3, no matter how, not important which is which. And if you go back and see the selection rules and the probability amplitude, you see that the probability amplitude is increased when you have a larger delta J. So the argument is that by introducing an electric field parallel to the triangle, we deform magnetically, not structurally, magnetically the triangle, and we increase the probability amplitude. So then we're very happy with that. Then we thought about doing it with the chromium triangle, but the crystals were parallelepiped. It didn't give the same ease of manipulation. So we went to pulsed EPR experiments in solution, which opens up also other possibilities. So you just dip the electrodes in your deuterated solvent solution, you freeze, you don't want to do electrochemistry, and you apply an electric field. We did some electrostatics analysis to see what's the shape of its electric field. So it's not a perfect parallel plate capacitor. So you have, but you do have a region here that is relatively homogeneous in terms of direction and intensity. So it's good enough. It's good enough to do the experiments we did. So this setup gives you the ability to discriminate for various orientations of your molecules. So you have the Zeeman field here. So when you have your main axis, you have the G perpendicular, the G parallel, and then you can, these are the electrodes here, and you can twist, you can turn the sample holder, and you can have different orientations of the electric field. So you can have it's a very simple setup, but it gives you high degree of discrimination for various orientations. So the simple experiment is, the simplest experiment that we did was this Han echo, where we interjected an electric pulse between the microwave pulses. This is a modification of MIM's initial experiments. And you see here that very easily, you see that the iron triangle has shows a decrease in the intensity of the echo. And then by increasing the duration of the electric pulse incrementally, we were able to monitor the effect on the echo intensity. These are the echoes, and this is the integrated intensity. In the G parallel orientation at about 3,300 Gauss, you get this behavior, but when you go to about 4,500, the G perpendicular orientation, you get a precipitous decrease and then oscillations. And you can see it better in this scheme here. You have the echoes. And actually, you see that with purely electric means, we can reverse the direction of the magnetization. So that was an interesting finding. So then we went further on to further increase the duration, go right up to the echo. In theory, what you do here in the defocusing period, you should cancel out what here in the refocusing period, and that's indeed the case. So these are the field sweep echo detector experiments that as a function of the electric pulse duration. And here these are the spectra, and these are slices at specific magnetic field values. And you see here that at the G perpendicular, you have an oscillatory behavior. And when you turn the sample holder, so you from E perpendicular, you go to E parallel, you still qualitatively get the same thing, but the oscillatory behavior is somewhat different. That piqued our interest. So we focused here and we did more detailed experiments. So we varied the voltage that we applied. And here you see that we have those oscillations as a function of the voltage. And these are the Fourier transforms of those curves. And you see that we have not just one, but apparently two, at least, frequencies. And we were able, and if you plot these data as a function of the duration times voltage, all curves collapse into two families, the perpendicular and the parallel. And they are directly proportional to this quantity, which means that the effect is directly proportional to the electric field strength. And you can actually fit the frequencies, they are perfectly linear. So the next step was go to the chromium complex and see what happens in that case. So it's a very short story. Almost nothing happens. You need very detailed statistics just to get a hint of an effect. So let's say that the effect is negligible. So why? So what is the mechanism behind the effect that gives this effect in iron and not in chromium? In multiferroics literature, there is a lot of there are a lot of mechanisms trying to describe the interplay of magnetic couplings and electric polarizations. And a very popular model is this here. It's the KNB model by Katsura, Nagaosa, and Balatsky. And it's very nice because it's a very simple in its formulation. It says that you have an electric polarization, P, that forms through the interspin interaction. And it's proportional to this quantity. It's actually very simple to just take your spin Hamiltonian parameters, calculate here we treated semi-classically the spins, and you can calculate the vectors and calculate the polarizations predicted by this theory. So so what is interesting is that the net polarization is a function of the orientation of the magnetic field, which explains the anisotropy of the effect between G parallel and G perpendicular. So in the red, you have the interside polarizations. In blue, you have the net, the sum of the polarizations. And like this, it's not very clear, maybe. You can draw some videos of what happens when the magnetic field rotates. So I just gray out and leave this, which is the most indicative. So you have magnetic field in plane, and you have nothing happens to the polarization. But here you have the 2 weak, 1 strong magnetic couplings. When we switch to the 2 strong, 1 weak, you see the polarization has switched orientation from here to here. And then when you lift the magnetic field outside the triangle plane, you can modify the intensity of the polarization. And when you go to this direction, it can also go outside the triangle plane. So that's a very qualitative model. It happens to fit the data at a qualitative level. So to sum up, we have a very strong effect in the iron triangle. We see that with continuous wave and pulsed EPR experiments. We have practically no magnetoelectric coupling in the chromium triangle, which means that we have a correlation with the Dzielodzhinsky-Moreia and delta J magnitudes in the two complexes. And here I would like to draw a parallel with a previously published work by Liu Ardavan and Winpenny and others, where they studied this copper triangle, and they associated a magnetoelectric effect with degenerate frustration. So very weak delta J and negligible antisymmetric exchange, which makes this complex more similar to our chromium complex. So it's probably the case that in our case, there's a different mechanism than in this case. So these are the first pair of results in different systems, and maybe there is more underneath the surface. So I would just like to stop here and mostly thank the group in Strasbourg, Philippe Turek, Jérôme Robert, and Nathalie Parizel, who collaborated in this work. I will stop here, and maybe now we can discuss.
I have to applaud for everyone, but I'm sure, thank you for your talk.
Time-wise, I don't know how I did.
That was perfect, even on the short side, I guess.
Yeah, okay.
But then we have time for discussion. So now, if you have questions, you can go to the participants panel, and you can raise your hand so I can see it, and then I say your name. And now I will also allow that you can unmute yourself now. Okay. So any questions? Then maybe I start. So it's a very actually, Thomas.
Hey, sorry, just curious question because I don't know anything about it. So, so you had your compound, you put it in the EPR tube, and then you put in your electrodes inside the EPR tube for the pulse EPR experiments.
Yes, yes. You just if you put the electrodes inside the EPR cavity, the EPR tube, and then inside the EPR cavity.
Or then you just apply a field while the magnet is on as well. So
yes,
then the calculation you showed was like also like how the electric field and the magnetic field work together as well. Or isn't the electric field also coupled to the magnetic field, the external magnetic field?
No, the two are they work independently. So you have the Zeeman field from the electromagnet, and you have the electric field from the electrode.
Yeah, okay, got it. Okay, great. Oh, by the way, I love the
your connection is a bit bad, I think, Thomas.
Iron triangle.
Maybe you can turn off your video.
Or put it in the chat, Thomas. You'll love something. I think that's what I got from it. So maybe we just continue. Ilya.
Athanassios, nice talk. I have an educational question. This magnetoelectric coupling itself, where exactly does it come from? Is that this famous angular magnetoelectric term that comes out of Dirac's equations that everybody ignores, or where physically does it appear when you start eliminating, let's say, the negative energies from Dirac's equation and going into, spin orbit Zeeman and so on? Is it coming from there? Is it some kind of effective coupling?
Yes, I don't know. I cannot go this much backwards in basic theory, but to answer the question, to have according to these calculations, these models that I showed you, you need the Dzielodzhinsky-Moreia term for any magnetoelectric coupling, any electrical polarization to come along, which is a relativistic effect. So
right. That answers it.
Yeah. So yeah.
Okay. Thank you. Any other questions? So maybe I have one. So basically, so where do you want this to go, or what's the? Are you also just interested in synthesizing these compounds that have this coupling for using it for some kind of technology, or is it also just fundamental question, basically, how these how you can derive this from the structure, or like?
Well, of course, it starts from the fundamental. Why, when, how does this happen? Now, in terms of applications, you just saw that one of the ideas behind this is trying to store information that does not decohere from magnetic noise. But the fact that you have 2 degrees of freedom coupling to one another, the magnetic and the electric polarization, it gives it might give other ideas, like to sense, to make sensors from out of these molecules, or detect and use. Actually, we're working on an idea right now to try and detect magnetic molecules through the change the dipolar interactions provoke to the electric properties of magnetoelectric triangles. But the basic motivation for me is the fundamental theory. Then, of course, we can think of many ideas.
So, any other questions?
Thanasi.
Hi, Rafael.
If you wanted to maximize this effect, how would you modify your molecule? Or what would be your dream molecule to study?
Well, I mean, the model says big Dzержinski-Morillo and big magnetic asymmetries. So, in theory, I would say that I would take this molecule, the iron molecule I showed, and stick an axial ligand somewhere and make the equilateral geometry isosceles. So I would make the I would try to make the magnetic triangle a little more less equilateral, and maybe that would further increase the effect.
Well, we may have one of these molecules. I'll talk to you.
Okay. Okay.
I'm not entirely sure if this is a raised hand because it's another sign. But Shreya, do you have a question, or is this an applause?
Oh, it was just an applause. So
okay.
Maybe I got it mixed up.
And same question to Logesh. So do you have a question, or is that also? Okay, I guess it was not a question.
Yeah, it was an applause. Yes.
Ah, okay.
Hi, thanks.
Hi, Logesh.
Hi, Athanassios. Good talk. Thanks.
Chris, you raised your hand, but you lowered it again.
I have a question. In fact, I have two questions.
Yeah.
So first question is, I'm interested to know that, so once you put the electrode inside the cavity, isn't it the matching of the cavity is a nightmare?
No, actually it was much easier than we thought. At the beginning of this work, we were saying that it would be hell. We just stuck a few copper wires on an EPR tube and saw that doesn't really perturb the cavity.
So is it to be super thin or something like that?
Well, it's the electrodes I put here were 1/4 millimeter thickness.
Okay.
The thing is, the electrodes go parallel to the B1 field.
Okay.
And maybe, I don't know if that is actually important, that you have the plates of the capacitor like that. So the B1 field is parallel. If you had your electrodes like that, I don't know what would happen. Maybe there would be some Faraday effect that would shield from Faraday shielding. But actually, I didn't try this configuration. We always went with this configuration, and it worked just fine.
My second question is that, so all your field is a DC field, right?
No, yes, it's DC, static DC and pulsed DC.
Yeah, but anything with the, if you apply AC field, I have no idea about the frequency of the AC, like what frequency would be useful, but just
well,
any study.
In Florence, they did some electrically modulated experiments but the thing is that here, when you modulate the electric field, you don't change anything in your sample. If you saw the G value is not it doesn't change at all. So what in the DC experiments we saw an increase in intensity. In this work by the Sesoli group, they were changing the G as a function of the modulated electric field, and moreover, to get this kind of intensity with modulated electric fields at 1,000 volts, 2,000 volts, I don't know if it will have a generator that can produce that.
Yeah.
Okay.
Yeah.
Then Kelsey?
Yeah, hi. So really beautiful work. And I don't know if my question is really within the scope of what you're considering.
Should I stop sharing the screen because I can't see anyone?
You can, on the top right, you can even, you could put it as you want, but you can also stop sharing if nobody has a question to the sharing itself.
So more. So just go on with the question.
Yeah. So I might not be within the scope of what you're considering, and I understand that the origin of the different magnetoelectric effect in the chromium and iron triangles is a source of their different delta J's and G. But what do you think is the microscopic or the orbital origin of that difference between these two very similar triangles?
Yeah. So what I think is that, first of all, we don't have, any translational degrees of freedom at play here. It's not that we apply an electric field and we move physically the atoms and the nuclei. I think that the electric field moves just the electrons around the atoms. So it influences the way the spin densities also are arranged around the molecule. So microscopically, I would say this is the case, but I do not believe that we have the case of physically moving the atoms with the electric field. But that's a very intuitive understanding.
Thanks.
So could you see this, that this happens with, like, I don't know, IR or something like this under electric fields, or are there people looking into this?
Well, we are IR under electric fields. That's a nice idea. Actually, what we're planning to do right now is to try to do IR between those states. So in the iron triangle, these are in the far IR regime. So to do this with EPR techniques, even high frequency EPR, it's a little tricky. So we're trying now to see if we can have magnetic transitions between those two states that I showed in the Zeeman diagram. But that does not necessarily need an applied electric field. You use the oscillating electric field of the microwave of the electromagnetic radiation. So
Okay. Further questions? And maybe I still have one actually. So, when you apply the electric field, you get these oscillations. But you have a very inhomogeneous electric field.
Yeah.
Right. So do you think that basically if you could apply a very homogeneous field, that you could somehow really like coherently,
yeah, so actually
make echoes and everything? And
yes, so I have a slide here. So
okay.
This is an overlay of the statistical distributions. These are the bars at various voltages from 300, from 300, 500, and 950. And these are the Fourier transforms of the oscillations at the E-parallel orientation. So it's not perfect, but there is a correlation. So you can see as I said, the intensity of the electric field influences the frequency. So as you have a distribution of electric field intensities, it's logical to expect a distribution of frequencies. So this is what you get. So in theory, and this is like the Deer experiment. So you have a distribution of a perturbation and the distribution of frequencies. And what you're doing with Deer analysis is something similar to that. Actually, I did try to put the traces of the oscillating traces to Deer analysis and try to see if we get any qualitatively any conclusions. Okay, that was just for amusement purposes. But yes, if you had a perfectly parallel plate capacitor, I think that you would have a single frequency.
Okay, and then Maria had a comment. So I think you can unmute yourself if you.
You hear me?
Yes.
Hello?
I just wanted to add a question about the CW, let's say EPR that you can do by applying an electric field, and instead of modulating the magnetic field as you do in normal EPR, you modulate an electric field. And you do a phase sensitive detection as in normal EPR, but instead with the in phase with the electric field modulation. So I think that it's not true that you are only sensitive to a change of the G value in which may be induced by the electric field. And indeed, what we have published on a magnetic chain, it was an effect on the exchange interaction, which was induced by the electric field. But occasionally in this system, this could be corresponded to a change in the G value. But now we are also investigating other systems. In one case, we observe change in G values, but also we have simulated what we would observe in case of real change in the exchange interaction. So I think that in principle, you can observe also with CW electric field modulated EPR a change in the exchange interaction.
Okay. Well, I extrapolated from the fact that your system was quite different from ours. So it's an extrapolate that maybe the two methods are not, this method is not compatible with ours, but yeah, maybe it's, of course.
Yeah. No, I think they are. I mean, it's nice to compare the two.
Yeah. Yeah, but of course it's a very different experimental setup. So we went to another direction. So there was a choice at some point how we're going to tackle the problem.
In which sense, sorry, it's different?
So, I mean, experimentally, it's I suppose it's not the same thing to have a modulated electric field from a pulsed electric field. So it's a slightly different protocol.
All right. Thank you.
Thank you.
Okay. More questions? I don't see any. Thomas?
Yeah, can I? So I'm a stupid biochemist. So I'm gonna ask a really dumb question.
I'm a stupid chemist.
It's fine. It's fine. I have a really dumb question.
Thomas, maybe stop your video.
I don't say. Is that better?
Yes.
Yeah.
Okay. I'm a stupid biochemist. I have a really dumb question. I don't know if it makes any sense, but since nobody asked any question, I might as well come up with some fluff in my head. If I have a protein sample and there's a whole bunch of MDSLs on there, let's say 2, 3, 4 MDSLs, and I put my my sample in the tube and I put some electrodes in there, just the same setup as you had. As I increase the voltage, I apply electric field in the tube. So I can modulate the G values of all of the individual MDSLs. That should give, when I do that, then I should get an orientation when I measure, for example, dipolar coupling as a function of the electric field applied. Is that correct?
So you want to apply the electric field in the fluid solution?
Well, no, I'm going to freeze it. It's the same setup what you guys had. Just let's say I would do a d-arrhythmia sifter, anything of such a sort.
Well, I suppose to orient your molecule, you need also to have a fluid solution, right? I mean, even if there is a dipolar moment that will tend to physically orient your molecule, if it's frozen. But just to say that among the first experiments that were done with electric fields were on biomolecules by MIMS.
Okay.
One of his directions was impurities in oxides. The other direction was biomolecules.
Okay.
But yeah, to orient, I mean, you mean like you have liquid crystals that you orient liquid crystals in an electric field,
let's say,
right?
Yeah, I mean, why not? Let's say like we do the same thing like an RDC, where you have a media, you dump it in there, you can orient the biomolecules in some combination.
The thing is that you don't want to apply an electric field in the fluid solution because you will get electrochemistry.
Right. Okay.
So you might even oxidize the solvent.
Okay.
Depending on the voltage.
Yeah, that's true. Okay.
Okay. Any further questions? I don't see any. Then thank you again, Athanassios. Thanks everybody for the good questions and the discussion. I will stop the recording now.
Okay. Thank you very much.